So the last topic in the second unit is the relationship between shear force. Shear force, the load here is the shear force, shear force and UDL applied on the beam. What is the relationship between the load and shear force that are applied on the UDL on the beams? So point load ki shear force ki relationships enti. So that is the relationship between shear force and bending moments. So here, if you see the diagram, so a simply supported beam is there and a UDL is applied on the simply supported beam. A UDL is applied on the simply supported beam. So I am considering a small element D, that is C, C dash. C and C dash are the small elements, and at a distance of small x, and I am finding the shear force at a C and C dash. I am finding the shear force at a C and C dash. So it is a V, the shear force is V on one side, and V plus delta V, V plus delta V is the shear force on the other side, because the shear force will be increased due to this UDL on the other side. So small length dx is a length is available, dx is a length is available, therefore the shear force on the other side will be increased. Therefore I am moving from the left hand side to right hand side, amma. The section is moving from the left hand side to right hand side. Therefore the shear force at a C and the shear force at a C dash are V and V dash plus delta V. That is the 2. Already V will be existed at the C dash. This is the C and this is the C dash. So V and some more V will be added at a C dash. Therefore V plus delta V is the shear force at a C dash, and at a C it is a V. Similarly, I need to find out the bending moments at C and a C dash. So at a C, the bending moment is the bending moment is M. I am assuming as M. I am assuming as M, and M plus delta M is the bending moment at a C dash. So I need to find out the shear force and bending moments at a C and C dash. So I am considering only shear forces. I am considering only shear forces and balancing the forces applied on the small element length dx. Small element length dx. So here a UDL. Here a UDL is applied here. A UDL is applied here. Therefore, I am need to converting this. So that is W into delta x is the length, is the point load, which is shown in the red direction, red color, which is shown in the red color is a point load which is acting on here. Therefore, balancing the forces. So here we have V and V plus delta V are the two forces, and minus W into delta X are the other force, which is applied from the top to the bottom. So here balancing the forces, therefore V and minus V will be cancelled, V and minus V will be cancelled, and delta will be remaining, delta V will be remaining. So we are getting a equation delta V is equal to minus W into delta X. Therefore dividing both sides by delta X, therefore dV by dx is equal to minus W. So here V is nothing but a shear force F. V is nothing but a shear force F. Therefore, if I differentiate the shear force, I will get the UDL. If I differentiate the shear force, I will get an UDL. If I differentiate the shear force, I will get UDL. Now, balancing the moments. So here, M plus delta M is the one moment and M is another moment, and V into delta X into its distance is V into delta X, and its distance is delta X by 2. Therefore, balancing it, therefore M and minus M will be cancelled. Therefore, delta M is equal to, we'll get some equation that is 1 by 2 V into delta X minus 1 by 2 W into delta X square. Where delta X is very small, delta X square becomes very, very small. Therefore, I can neglect it. I can neglect it, this term I can neglect it. Therefore, I am getting delta M is equal to V into delta X. Therefore, again differentiating both sides, that is moving the delta X into this side, I am getting delta M by delta X is equal to V. Therefore, differentiating the bending moment, I will get the shear force. Differentiating the bending moment, I will get the shear force. So these are the relationships between the shear force and bending moment. This is the last topic in the second unit. Next, we are moving for the third unit, that is nothing but a bending stresses in the beams. So we need to find out the stresses. Up to now we have found out the movements and shear forces only under the beams. So movements antunnai, bending movement anta and shear force anta anedi maatrame kanukunnamu. Now we are discussing about the stresses. So how we can calculate the stresses in the beams. Beams lo ela stresses calculate cheyali enti anedi. So here two types of stresses are existing in the beams. One is bending stress, second one is shear stress. Bending stress and shear stress both are in the third units. We have two chapters. First chapter is how to calculate the bending stress, and the second chapter is how to calculate the shear stress while a shear force is acting on the beam. So beam having a shear force. The beam having a shear force, due to these shear forces and the loads, the beam bends. So this bends means we are getting a bending stress, and due to this shear force, a thrust force also will be created inside the beams, that we will call it the shear stress. Shear stresses will be created inside the beams. So I need to calculate the shear stresses and bending stresses in the beams. So first chapter in this third unit is bending stresses. So here we can see a tree and a branch. A load is applied on the branch. Therefore, a stresses will be developed in the branch. So we can see a similar diagram here. So here it is fixed at this point. And it is a free another end. And applying the load. That means it is a cantilever beam. So a branch feels like a cantilever beam. Whose cross section is a circular. But here a cross section will be a rectangular, a circular. A beam cross section may be a rectangular, a circular, a C cross section or a I cross section or a T cross section. So here a beam may have this type of cross sections. A beam may have this type of cross sections. So here, according to this cross section only, the bending stresses will be varying. Up to now, we have studied only the forces applied on the beams and how the shear force and bending moments, the bendings of the beams we have studied. But how we need to study the cross sections of the beams, and according to this cross section only, the stresses in the beams will be varying. The stresses in the beams will be varying. So here a small example of the bending stress is a beam is shown here. There is nothing but a bridge. A canal bridge is shown here. On the canal bridge, some person is moving. So a personal load is applied here. Therefore, due to this, a bridge will be bending. The bridge will be bending as shown here. So here a bending is occur. So due to the external load, a bending is occur due to the external load. Therefore, a bending stress will be developed in the bridge. Here we will call it as a beam. So in the previous diagram, it is a cantilever beam. In the previous diagram, it is a cantilever beam, and now it is a simply supported beam. Now it is a simply supported beam. It is a simply supported beam. So its cross section may be varying again. It may be a circular, it may be rectangular, it may be a circle, section according to your problems.
మళ్ళీ ఆయన మళ్ళీ కాలేజీ పోయి దాన్ని చదువుతారు కదే.
ఒకరోజు 10 to 11 చేసుకో. మీ నాన్న ఒకరోజు వెళ్ళమంటున్నారు కదా, రాని తెలిసిన రోజు
అదే.
So here, when a beam is loaded in the beam, when the beam is loaded and bends like this, so longitudinal bends into curve. So initially it is a longitudinally. Now due to this applied load, due to this external applied load, it will be bending like this. So we can observe a compression and a tension in the beam. So here upper layers, that is, while this is a neutral axis, we can draw a neutral axis. The upper layers feels a compression. That is, the length of the upper layer will be decreased. It feels a compression, and the lower layers of the beam, feel anxiety. So its length is increasing now. So we can see here, this is the layers, topmost layer. I need to move from the neutral axis. And the layers, upward layers, these are the layers. So the layers feels a compression. So if I move from the neutral axis to topmost layers, it feels a compression. If I move in this direction, downward direction, it anxiety. So when an external load is applied on the beam, so here small assumptions are need to be considered here, Small assumptions are need to be considered while deriving the equation, that is a bending stress. So before bending, initially it is a straight. Before bending, initially it is a straight beam. Initially it is a straight beam, and the cross sectional, that is the cross section of the beam, either it may be a rectangle or a circular, uniform cross section is exist. So throughout the length of the beam, throughout the length of the beam, throughout the length of the beam, the same cross section need to be exist. And it is a homogeneous, it is a homogeneous material, it is a homogeneous material, and it obeys the Hooke's law. It obeys the Hooke's law. What is Hooke's law, ma? Proportional to strain. Stress is directly proportional to strain up to the elastic limit. It obeys the Hooke's law, and it has the same elasticity modulus in tensile and in compression. It has the same elasticity modulus, that is capital E. Capital E. The capital E is same. The capital E is same for the compression and for the tensile tension. Both are same. We are assuming it, but it will not be same. It will not be same. We are assuming it is same while deriving this problem. While deriving this equation, we are assuming it are same. So after the bending, all loads are supported at the reaction polar, that is coplanar perpendicular beam. That is, after bending, we can see this type of a circular cross section. This type of a circular cross section is existing. So polar means coordinates. So here, while extending this cross section and extending this cross section, it will meet at a point O. After bending, I am assuming it is a perfect radius, that is a perfect circular bending is existing in a beam. After bending also, the cross sectional, the plane cross section remains a plane. That is, this is the plane cross section. The plane cross sections remains a plane. So it will not make any changes. But actually, the upper layers will be moving outside and the inner layers moving inside. But we are assuming it as a plane. It will be a plane. A straight plane is existing here also. I am assuming it. We are assuming it. The bending must be not have any twisting. Etuvanti twisting ledu. Beam lo etuvanti twisting ledu. And it has not exceeded the elastic limit. Elastic limit daati manam load apply cheyatledu. Elastic limit daati manam load apply cheyatledu. So they are the assumptions while deriving the bending stresses. So here very important point is neutral axis and neutral layer. Neutral axis and neutral layer. So in the engineering mechanics, we have studied the center of gravity and centroids. So the center of gravity means for a body which having a volume, will have a center of gravity. Centroid means for a cross section. Centroid means for a area. So here, this side area have a one centroid, this side area having another centroid. We have two centroids on the two sides of the areas. So while joining these two centroids, we will get an axis. That axis is called as neutral axis. So we can see a blue line which is joining two centroids. We have a cross section on this side, we have a cross section on this side. So by joining these two centroids, we'll get a straight line. That line we'll call as axis, and it is a neutral axis. Next, neutral plane. What is a neutral plane? Here plane represents a planema. So in a neutral axis, I need to draw a plane. So it is nothing but a layer. It having a length in my cross section. It having a length. This is the plane. It having a length. We can see here blue length. Blue length. Initially it will be a dotted. If it is a axis, will have only dotted, only dot. So if it is a line, means it is a plane. So neutral plane and neutral axis are the two fundamental points we need to remember here, Amma. So here the neutral layer and a neutral axis will not feel any type of bendings. So it is not changing its dimensions. Above the neutral layer only, above the neutral layer only, above the neutral layer only, or neutral plane, the bending will be occur. Here above the neutral layer we can see the red line, and below the neutral layer we have another lines. But in the neutral layer they will not have any type of stresses. So neutral layer daggara etuvanti types of stresses undadu. That means the bending stresses at the neutral layer, the bending stresses at the neutral layer is 0 Newton per mm square. So at the neutral layer will not have any type of stresses. That means there will not have any compression or a tensile at the neutral layer. So that a plane intermediate between the surfaces in change in length. So length will not be having any changes because there is no stresses on the due to this bending. So painemo compression feel avutandi, kindemo tensile feel avutandi. So our tension nundi compression ki vachevadiki madhyadarlo it changes its sign. That means at a 0. So the 0 will be occur at the neutral axis. The 0 will be occur at the neutral axis. So we will have neutral layer and neutral axis while deriving the problem or equations. So now, so external movement is applied on the beam. External movement is applied on the beam and resisting that movement. So to balance a resisting force need to be applied to that movement. So we have studied up to now. A load is applied on the beam. The load is applied on the beam. Due to this load, the bending, that is bending of the beam, bending moment will be occur in the beam. So the beam should not bend, means a resisting force need to be applied to unbend the beam. So there is a inertia force, we will call as a inertia force. The movement, internal movement resisting bending force is applied to make as a equilibrium condition. That is, the beam need to be straight. The beam need to be straight after the applying load also. So a resisting bending is applied here. So after, we can see this diagram. A cantilever beam is considered. A cantilever beam is considered, and a neutral axis is shown here, and the cross section is this. The cross section of the beam is this. Now, when the load is applied on the beam, the topmost layers will feel a tensile. That is, its extension of the layers is, we can see here, and the bottommost layers feels a compression. Now I am considering a small region, delta x region only. So initially it is a straight. So I am considering the small region, this is a small region I am considering this. So initially the topmost layer, here this is a topmost layer, and this is the bottommost layer. This is a bottommost layer, and here a black color is a neutral axis. A black color is a neutral axis, and I am considering a layer at a distance of y. At a distance of y, that is a red color, whose length is AB. Whose length is AB. Length of the layer is AB. Now I am considering this layer like this, above the neutral axis. So this is the layer at a distance of y. I am not considering the topmost layer, in between layer. I am considering in between the layer. So now before bending, this is the diagram before bending. Now after the bending, I can see the diagram here. The topmost layer is this. It is shifted to H dash and G dash. H dash to G dash. It is shifted to H dash and D dash. And the bottommost layer is shifted to E dash and F dash. E dash and F dash. And the considered layer AB is now A dash and B dash at a distance of Y. At a distance of Y from the neutral layer. At a distance of Y from the neutral layer. And now the neutral layer also changed as C dash and D dash. C dash and D dash. After the bending is occurred. After the bending is occurred. Therefore, I am extending the cross section. I am extending the cross section, and this side and this side. East side cross section extend jaste, it will meet at a point O. It will meet at a point O. We are assuming it. Now from the O, I am taking a radius to the neutral axis, that is small r. In the textbooks, it will represent as a capital R, radius of gyration or radius of curvature. Radius of curvature. Radius of curvature. So it looks like a small radius. So inner radius, outer radius, as well as middle radius. That is a midline radius. Now it is a radius from the O, and it is the angle between this plane, cross-sectional planes. Cross-sectional planes is theta. Now I need the length of the arc. Length of the arc. So we can calculate the length of the arc by using R into theta is equal to C dash and D dash. That is the length. That is the length of the arc, So it is geometrically we can calculate the length of the arc is equal to R into theta is equal to C dash and D dash is the length of the arc. Chord length, we will call it as a chord length. Similarly, we are concentrated on this layer. We are concentrated on this layer. Therefore, what is the radius of this layer now? The radius of the layer is R plus Y is the radius of the layer now. Into theta gives the A dash and B dash chord length. A dash and B dash chord length. So that is the Here he is explaining arc length is equal to radius into angle made. Angle made. This is the layer chord length. Now this is the final layer after the bending. Layer length of the fiber, that is the final length of the fiber after the bending. So if I need the strain in the fiber, so strain in the fiber is nothing but final length minus initial length by the initial length of the fiber. I am considering only AB fiber now. AB fiber only considered. Therefore, the final length is A dash B dash, A dash B dash, and the original length is AB by AB by AB. Initially, the AB length is also equal to CD. Initially, the AB length is also equal to CD, and therefore I can write it as C dash D dash, because initially we have observed that there will not be any change of length in the neutral axis. In the neutral axis, there will not be any change of length. Therefore, CD is also equal to C dash D dash. CD is also equal to C dash D dash. Therefore, I have converted this C dash and D dash by C dash and D dash. Now substituting the values, R plus Y into theta is A dash B dash minus R into theta by R into theta. Therefore, I will get strain in the fiber AB. The strain in the fiber AB is equal to Y by R. It may be a capital R or small r. In the textbooks, we are considering as a capital R. Now we know that Young's modulus is equal to stress by strain. Young's modulus is equal to stress by strain. Therefore, strain is equal to stress by Young's modulus. Stress by Young's modulus. Therefore, equating these strains. Therefore, we are getting stress by Young's modulus is equal to stress by Young's modulus is equal to Y by R. Y by R. That is sigma by E. That is stress in the fiber is equal to distance of the fiber by radius of curvature. Therefore, cross multiplying stress in the fiber by Y is equal to E by R. E by R. This is the first equation. Here, stress in the fiber sum, bending stress in the fibers. Some textbooks it will write as sigma B. Some textbooks it will write as a F. Some textbooks it will write as a F. So this is the stresses in the fibers. When Young's modulus and radius of curvature is known, when the curvature is known, we can use this formula. So another formula is there, the resting force. So here the diagram is shown that the stresses will be varying. The stresses will be varying when the distance is varying, because we have sigma B is equal to E by R into Y. So stress is directly proportional to Y. Stress is directly proportional. Here E will not be vary. It is a constant assumption. We have assumed it as constant, and a radius is somewhat a constant, therefore it will be varying amount. Both are a constant, so it is varying only on y. So if I increase the y, the stresses will be increased from the neutral surface. So I can see here it is initially low and increasing and increasing and increasing and increasing on the compression side. This is a compression side, and this is a tensile side. So we can see here it is increasing, it is increasing, it is increasing, it is increasing, and it will be increased at the topmost layer. It will be increased at the topmost layer while we are moving away from the neutral axis. Neutral layer or neutral axis. Next, second equation. So resisting force in the beam. So we will call it as a bending formula, and we have derived the cross section. The cross section of the beam may be this type of a lamina. And we are considering only a fiber AB. So this is the neutral axis, and this is the fiber. This is only fiber AB. I am considering this only fiber. The fiber area, this is the B side, this is the B side, and A will be other side. This is the B side and this is the A side. So I am considering only one thin layer, and this is the cross section I am showing here. This is the cross section I am showing here. So now the stress in this layer we have found. Therefore, it is nothing but E into Y by R is the stress. So this is the stress sigma on the layer AB. So now I am converting this sigma into force. Therefore, force is equal to stress into area. So what is the area of the fiber is dA. The area of the fiber is dA. Therefore, force is acting now in this direction, perpendicular to the board. Therefore, that is the force applied on the fiber above the neutral axis. Therefore, I can substitute this sigma value now. That is E into Y by R into dA. E into Y, whatever we have proved in the equation 1. I have substituted the value. That is the force applied above. This is the force applied above the neutral layer. Now, I need the moments about the neutral axis. So the moment is nothing but force into perpendicular distance. That is the moments. That are the moments applied about the neutral axis. Therefore, force I know now. I need to multiply the distance. That is nothing but at a distance. It is at a distance of y. This layer is at a distance of a y. Therefore, the moment, bending moment that is on this layer due to this force, neutral axis ki yanta bending moment istadi ante F into y. F into y is the moment. So therefore, the moment, small moment applied on the neutral axis. The small moment applied on the neutral axis is due to this force. Is F into dF. Is the moment. Now substituting the dF value. Therefore, I will get dm is equal to E into Y square by R into dA. that is the small movement occur due to this small force. So ilanti layers పైనుండి కింద దాకా చాలా ఉంటాయి. ఇలాంటి లేయర్స్ అబౌవ్ ది న్యూట్రల్ యాక్సిస్, ఐఎమ్ కన్సిడరింగ్ ఓన్లీ అబౌవ్ ది న్యూట్రల్ యాక్సిస్, ఇలాంటి లేయర్స్ చాలా ఉంటాయి. దేర్ఫోర్ ఐ నీడ్ టు ఇంటిగ్రేట్ ది స్మాల్ dm, that is the movement due to the layer AB లేయర్ వల్ల వచ్చే మూమెంట్ మాత్రమేనమ్మా ఇది. సో ఇలాంటి లేయర్స్ వల్ల వచ్చే మూమెంట్స్ చాలా ఉంటాయి. సో ఈ లేయర్స్ అన్నిటిని ఇంటిగ్రేట్ చేయగలిగితే సో ద టోటల్ మూమెంట్స్ అబౌట్ ది న్యూట్రల్ యాక్సిస్, ద టోటల్ మూమెంట్ అబౌట్ ది న్యూట్రల్ లేయర్ or neutral axis is nothing but integrating E by R y square dA. So E and R are constant, making outside, therefore E by R integral y square dA. Integral y square dA is my equation. So we know that integral y square dA is nothing but Ixx. We know that integral y square dA is nothing but Ixx. Therefore I can substitute now ER into Ixx. E by R into Ixx. Now I can move this side, that is m by I is equal to E by R. Is the second equation. Now we need to equate the 1 and 2, because both sides we are having E by R only. Equating 1 and 2, we are getting m by I is equal to sigma by y is equal to E by R. కొన్ని టెక్స్ట్ బుక్స్ లో m by Ixx is equal to f by y is equal to E by R అని కూడా ఉంటుంది. So this chapter having only this equation, this chapter having only one equation, very important equation. We need to by heart it. How to by heart it? ఎలా by heart చేయాలమ్మా? So here a thumb rule. Yes, a thumb rule means how to by heart it అమ్మా. జస్ట్ by heart చేయటానికి మాత్రమే ఈ స్టేట్మెంట్ ఉపయోగపడుతుంది. May I follow you, Elizabeth Rani. May I follow you, Elizabeth Rani. Here M represents the bending moment and maximum bending moment. M represents the maximum bending moment. I represents the moment of inertia about the Ixx. The units will be meter to the power of 4, and the stress, it may be a sigma b. Some textbooks it will represent as bending stress as sigma b. Some textbooks it will represent F. So bending stress will be in Newton per meter square, and y is the layer distance from the neutral layer. Neutral axis nundi ekkadothe మనం stresses find out చేయాలనుకున్నామో దాని distance in meters, and E is the Young's modulus Newton per meter square. E is the Young's modulus Newton per meter square, and R is the radius of curvature in meters. So this is the only formula in this chapter. So only derivation and only formula in this chapter ma. ఈ చాప్టర్ లో ఒకే ఒక డెరివేషన్, ఒకే ఒక ఫార్ములా. ఓకేనమ్మా? So here another 2 marks question is section modulus. What is section modulus? Section modulus is represented as Z. It is represented as Z. Therefore, the section modulus is equal to Ixx by Y. Here y is nothing but a distance from the neutral axis. It is nothing but y is nothing but a న్యూట్రల్ యాక్సిస్ నుండి కానీ న్యూట్రల్ లేయర్ నుండి కానీ మన లేయర్కి ఏ లేయర్ అయితే మనం స్ట్రెసెస్ ఫైండ్ అవుట్ చేయాలనుకుంటున్నామో ఆ లేయర్కి మధ్యలో ఉన్న డిస్టెన్స్ని వైతో చెప్తాము ఇన్ మీటర్స్ ఆర్ ఇన్ ఎంఎంస్ ఆర్ ఇన్ సెంటీమీటర్స్. ఇట్ ఈస్ అ లెంత్. అండ్ ఐఎక్స్ఎక్స్ హ్యావింగ్ యూనిట్స్ ఆఫ్ మీటర్ టు ద పవర్ ఆఫ్ 4. Movement of inertia having a movement that is units of meter to the power of 4. Therefore, Z having a units of meter to the power of 4 by meter, therefore meter cube. The section modulus is nothing but a ratio. It is defined as a ratio of moment of inertia by y. Y is nothing but a distance from the neutral area, from the fiber, for the fiber. Therefore, I can write now. Initially, we have got that equation as, now I can write it as m by stress is equal to m into y by I. We have achieved this equation. Previously, equation మనం derive చేసుకున్నామా, bending stress is equal to m by y. Now y is removed and placed at this position. Therefore, I can write it as m by z. Stress is equal to m by z. Stress is equal to m by z. So m is equal to stress into z, where z is section modulus. ఇక్కడ ఇంకో మాడ్యులస్ మనం కనపడింది. సో ప్రీవియస్ క్లాస్లో 4 మాడ్యులస్ చదివామా. యంగ్స్ మాడ్యులస్, షియర్ మాడ్యులస్, బల్క్ మాడ్యులస్, అవి ఎలాస్టిక్ కాన్స్టెంట్స్. ఇంకో మాడ్యులస్ చదివాం, ప్రూఫ్ మాడ్యులస్, రెజొనెన్స్ ప్రూఫ్ మాడ్యులస్, స్ట్రెయిన్ ఎనర్జీలో చదివాం. రెజొనెన్స్ ప్రూఫ్ మాడ్యులస్, స్ట్రెయిన్ ఎనర్జీలో చదివాం. ఇది 5th మాడ్యులస్, సెక్షన్ మాడ్యులస్. It having units of meter to the power of 3. So ఇక్కడ only 2 types of beams problems చేసేటప్పుడు, first one is a cantilever beam, second one is simply supported beam. First one is a cantilever beam, second one is a simply supported beam. So cantilever beam మీద external loads పడితే, the topmost layers feels a tensile tension and the bottommost layer feels a compression. So y పైకి వెళ్ళే కొద్దీ క్యాంటిలివర్ బీమ్ లో టెన్సైల్ గా కన్సిడర్ చేయాలి. y నెగిటివ్ తీసుకునే కొద్దీ, మైనస్ y నెగిటివ్ తీసుకునే కొద్దీ కంప్రెషన్ గా తీసుకోవాలి. y minus తీసుకునే కొద్దీ కంప్రెషన్ గా తీసుకోవాలి ఫర్ ఎ క్యాంటిలివర్ బీమ్. If I am considering a simply supported beam, the bottommost layers feels a tensile. The bottommost layer feels a tensile and topmost layer feels a compression above the neutral axis. If I am considering neutral axis, if I am moving the y downwards, I need to consider the positive tensile. If I move y upwards from the neutral axis, I need to consider as a compression. A negative stress will be developed. A negative stress will be developed on the topmost layer. The bending stress will be a negative because it is a compressive, and the bending stress will be a positive bending stress. A positive bending stress will be seen in the bottommost layers. So ఈ రెండు కాన్సెప్ట్లు ఒకటే. ఫస్ట్ ఏంటంటే మే ఐ ఫాలో యూ ఎలిజబెత్ రాణి. This is the only equation in this chapter. And second we need to by heart here is two concepts. So that is a cantilever beam and a simply supported beam. సో పైకి వెళ్ళే కొద్ది కంప్రెషన్ వస్తుందా టెన్సైల్ వస్తుందా అనేది మీరు కన్సంప్షన్ తీసుకోవాల్సి వస్తుంది. సో విత్ దిస్ వీ కెన్ సాల్వ్ ఎనీ టైప్ ఆఫ్ ప్రాబ్లమ్ యూజింగ్ దిస్ టూ కాన్సెప్ట్స్. So using this formula and a concept of these two, I can solve any type of problems. The bending stresses in the beams can be solved easily. So with this, a derivation of the first, that is the third chapter, the third unit, first chapter is completed. Third unit, first chapter is completed. So we need to do a problems on it. మనం దీని మీద ప్రాబ్లమ్స్ చేస్తే సో ఓన్లీ 2 periods is required to complete this chapter. ఓకేనమ్మా. సో రేపు కాకుండా ఎల్లుండి తోటి ఈ చాప్టర్ క్లోజ్ అయిపోతుంది. అండ్ నెక్స్ట్ వీక్ వీ విల్ హ్యావ్ ఎన్ ఎగ్జామ్స్. సో మొత్తం 3 units మీద కూడా ఎగ్జామ్ కండక్ట్ చేస్తానమ్మా. 3 units మీద కూడా ఎగ్జామ్ కండక్ట్ చేస్తాను. నెక్స్ట్ వీక్లో we'll have an exam on the 3 units. 3 units మీద ఎగ్జామ్ ఉంటుంది. 3 units మీద ఎగ్జామ్ ఉంటుంది. సో ప్రిపేర్ ఫర్ ఇట్. సో ఈ వీక్ లో సాటర్డే కూడా ఇది అయిపోతుంది కాబట్టి వి మే హ్యావ్ ఎన్ ఎగ్జామ్. సాటర్డే కూడా ఎగ్జామ్ పెట్టుకోవచ్చు, ఛాన్సెస్ ఉన్నాయి. సో ప్రిపేర్ ఆల్ ది టాపిక్స్. సో మీకు ఆల్రెడీ యూనివర్సిటీ క్వశ్చన్ పేపర్స్ ఇచ్చాను మీకు, అండ్ మెటీరియల్ ఇచ్చాను అండ్ టెక్స్ట్ బుక్స్ ఇచ్చాను. సో యూజింగ్ దిస్ యూ నీడ్ టు ప్రిపేర్ ఫర్ ది ఎగ్జామ్. So it may be a multiple choice questions answers కింద ఉంటాయి, but the question may be a problem. క్వశ్చన్ అనేది ప్రాబ్లం అయి ఉంటుంది. ఆన్సర్ ఏది అనేది మీరు మల్టిపుల్ చాయిస్ పెట్టాల్సి వస్తుంది. సో ప్రిపేర్ ఫర్ ఇట్. So with this I am concluding this section, amma. With this I am concluding this section. So any doubts about the question papers, so please consult me.
అన్ని కొడతావా అన్ని మరి